We're continuing on with kinetics here. We got just a little bit to finish. We're talking about reaction mechanism, and then we're going to roll into next chapter, which would be 13 and equilibrium. So at the end there, we were talking about reaction mechanisms, and remember that basically reaction mechanisms basically are sort of pathways by which reactions can occur. They oftentimes will occur through perhaps what are referred to as elementary steps. And we could add these elementary steps together to get our overall reaction, which in this example here would be this. Now, when we do these sort of mechanisms here, it is the one and only place where we can actually write rate laws for these elementary steps, and we can use the coefficients to write it. So we could write for this one, the rate is equal to K times C times D. This guy up here would be the rate is equal to A times B, basically. So the one place where you can use the coefficients there, and that should have a K, is when we're doing these elementary steps. There's a really important step within the mechanism usually, and that is what is referred to as the RDS, which is the rate determining step. That is basically the slow step in the mechanism. So it could be labeled as slow, and then you know that's the rate determining step. The rate determining step should always have the same rate law as the one found experimentally. So a lot of times in mechanism problems, they'll tell you experimentally the rate law was found to be this. The step that has a matching rate law allows us to know that that is the rate determining step. When we want to know whether or not a mechanism is good, there's really a couple important things that need to happen. First off, when you add up all the steps and cancel out the intermediates, it does need to equal the overall reaction you're looking for. The other important thing is what I just mentioned there. When you write the rate law for the rate determining step, it does need to match the one found experimentally. So if those two things are good, when you look at a mechanism like we kind of did towards the end there, then you know it is a probably a good mechanism or a possible mechanism for that reaction. Again, doesn't mean it will always occur that way, but it means that it is possible that it could occur that way. If you add up all the steps and it does not equal your overall reaction, or you find the rate determining step has a rate law that is different than the one that's found experimentally, then either one of those things would mean that it was a bad mechanism and really is not a plausible way that a reaction can take place. Any questions on that there? All right, so we were doing one at the end, and we're going to kind of look at it here together. You should have gave it a go. So in this particular mechanism here, we want to determine whether or not it's sort of a good mechanism or a bad mechanism. So again, the first thing that we want to make sure of is when we do add these two steps together, that we do end up with the same overall reaction. And in this particular case, it looks like perhaps the O will cancel in both cases. That will leave me on the left-hand side of the arrow 203, on the right-hand side of the arrow 302. So that obviously does match the overall reaction that we're looking for. So far, that's good. We could easily determine which one's the rate determining step here, and it is which step is the rate determining step. Which step? It is the second step, right? It is the one that is marked slow. So that would be our rate determining step. That means that this step here, we want to write the rate law. And if we write the rate law for that step, it's going to be K times O3 times O. The experimentally found rate law is right here. And at this point, we would want to look at both of them and see whether or not they match. And as we talked about last time, you really cannot compare directly both of these rate laws at this point, because in the rate law that we just wrote for the rate determining step, there is the intermediate. So we have this intermediate that's there. So that doesn't really allow us to compare sort of apples to apples. So we are going to have to do a little bit more math here to get rid of the intermediate in that rate law. And that's where we're going to then go to our first step in the mechanism. Our first step in the mechanism is a reversible reaction, which means it will eventually come to equilibrium. That means there's a forward direction heading from reactants to products, which I could write the rate law for that, which would be the rate of the forward direction would equal K times O3. Could also write the rate for the reverse direction, which means our products going to reactants. In that case, our products are actually going to be like our reactants. So it would be K times O2 and O. Any questions on that there? Now, because this first step is a reversible reaction, as we talked about last time, although we do not really know what that number is, it should be the same number for both of them. So this number here should be the same. And what that really allows us to do is actually set the back end of these guys equal to each other. So we could say KO3 is equal to KO2 and O. Remember, our goal here really is to sort of substitute out for O. So we're going to divide K and O2 to both sides. Those guys will cancel. And what that will give us is that O is equal to K times O3 divided by K times O2 in this particular case. Any questions on that so far? Now, pretty much what we just solved for is what O equals. So we're going to take pretty much what we just solved for, and we're going to basically substitute it in over here for our O. And if we do that, we now get a rate law that really will not have the intermediate in there anymore. And if we do that, we will get that the rate is equal to K times O3. I'm just going to substitute in what I just wrote there, K times O3 divided by K times O2. Doing a little bit of cleanup here, all the little K's are rate constants, which means they all should be the same number, so we could cancel out a couple of those. We also have O3 on top times O3 on top, which gives us O3 squared, which would reduce us down to O3 squared divided by O2 as our rate law. So what we want to know is, does this and this, do they match? Are they the same? The answer is they actually are the same, because the O2 in the first one is to the -1, which means anything to the -1 is 1 over it. Yes. Times K and O3 squared. So it actually is the same, yeah? Even though it may look slightly different, but the -1 there means 1 over it. Yes. Yeah, so like here, is that what you're talking about? The one right above, like right here? Yeah. Right next to it. Here. Yeah. Okay. Are you asking how can I set those equal to each other? Is that what you're asking? Yeah. It came from before that. Basically, we took this guy and we took this guy here and we put them equal to each other. So what we had was K times O3 is equal to K times O2. And O. So we're just isolating the O. So that's why we divided that to the other side, basically. And it would cancel out, obviously, on the right-hand side like it did. And then it would be remaining on that side. Yeah. Other questions on that? So in this case, it actually does match. So this is a good mechanism. Right. Any questions on that there? Yeah. Yeah, so once you get rid of in the rate determining step, if there happens to be a intermediate, for example, in it, and you substitute out the intermediate for things that are not intermediates, at that point, once you're done substituting out, if the two rate laws match, then it is good mechanism. If it does not match, then it's a bad mechanism. And the other thing that can make it a bad mechanism is just right off the bat, you add up all the steps and it doesn't give you the overall reaction. So that could happen as well. You take a bunch of steps out of together and go, that is not the reaction that I'm looking for. So that's the other thing that can kind of make it a bad mechanism. Other questions on that? All right, so one last one here, determine the overall reaction, the rate determining step. We'll go with that. I got mixed up. I think it's okay on your paper. And the rate law, and identify any intermediates in here. So give it a second there and see what you come up with here. Okay, let's take a look. So first off, the overall reaction is pretty simple. We're just gonna add these guys together. In this case, it looks like B will cancel, and I think that is it. Everything on the left-hand side of the arrow will stay on the left-hand side. Everything on the right-hand side of the arrow there will stay on the right-hand side. So if we do that, we end up with, looks like a 2, maybe, try it again, 2A plus B2 goes to 2AB would be our overall reaction there. We could also see from crossing out there, it looks like that our intermediate is actually B, right? That was the only thing kind of crossed out completely. Remember that an intermediate needs to be fully gone, right? And it should not appear in the overall reaction when you do cross them out. Which one would be the rate determining step? Would be first one would be our rate determining step. Because we know this is the rate determining step, that means that the rate law for that step should really be the rate law for the reaction. So we would just write the rate law based off of that. And the rate would equal K times A times B to the 2 in this case. Any questions on any part of that there? Any questions on mechanisms? Okay. So what does that really mean? For example, if we had, zoomed in there, if we had sort of a two-step process in terms of energy. Well, if we look at like an energy diagram, for example, and let's just say we had, say, our reactants, right? And we did this move here. And I'll say this is our products, right? So let's say this was a two-step. Let's say this was a sort of a two-step mechanism where this right here would be the activation energy, right, of step 1. And this right here would be the activation energy of step 2. Which one is larger? The first one. So we would make sure that that would probably be our rate determining step, right? That's going to be the larger hill that has climbed. Now, if the second step happened to be the rate determining step, then we would expect to see the second step have a larger hill, right, to climb to get to the other side. So, you know, if this was like our made up one I did the second ago, where it's like C plus D goes to C plus D goes to E plus F, this would be like A plus B, right? And then our C and D would be formed over here, right? And then our products would be our E plus F kind of coming out at that end. And again, that would be sort of how you would draw an energy diagram to represent sort of the mechanisms and the difference in the energy of the first step and the second step, and which one is slow and which one is fast. Any questions on that there? Overall, this reaction would still be the way I drew it, exothermic or endothermic? It would still be exothermic. Reactants are higher in energy than our products, right? So this is a way that you can, again, demonstrate, you know, what's happening in a mechanism with an energy diagram by drawing something like that. Any questions about that? Now, you know, if you ended up maybe here, maybe, you know, we had something like and say this is our reactants, that's our products. We'll call this step 1. And this is step 2. In this case, if we were comparing, right? Ish. Almost drew them about the same. Roughly speaking, which step would have the bigger energy hill? The second one, barely. Not the best drawing, but you get the idea. So in this case, right, the step 2 would probably be our rate determining step. Once again, though, the overall reaction here would be exothermic or endothermic. This would be endothermic, right? Again, the position of those guys. So you will be asked to draw some of these energy diagrams. You should know how to do them. I think specifically the next experiment we do, there's a bunch of post-lab questions where they want you to kind of sketch these type of things. So this is how you kind of go through it. And really it's just the size of the hills, right? Based on which one's a slow step and which one is obviously the fast step. Any questions on that there? Yeah. Last thing we talked about, we talked a little bit about it earlier, but a catalyst again is a substance that's added to a reaction. Once again, it is not a reactant. And again, it's not a product. And it does not get used up. In a reaction. A catalyst really is there in most cases to facilitate the reaction occurring faster. And it could be multiple ways it's able to do that. But it really, for the most part, finds a much more efficient way for that reaction to take place than if the catalyst was not present, and it would take a lot longer. So for example, it may be something like a solid that's a catalyst, and maybe the solid is something that will sort of attract gas molecules to it, for example. So now you get everybody sort of in a centralized location. It's going to allow obviously collisions to occur and reactions to start to happen a lot faster than everybody's just kind of flying around randomly trying to find each other. So a lot of times, you know, just kind of find a much more efficient pathway. And ultimately what that does is it finds a much better pathway in terms of energy for those reactants to get to the other side. And the result of that is that it usually will lower the activation energy. So usually it will lower that activation energy. So instead of having to climb this big hill to get to the other side, by adding the catalyst, we have significantly decreased the hill sort of requirement to get to the other side. The result of that is you're going to find a lot more reactants having sufficient amount of energy to get to the other side. And the ultimate result of that would be you would expect the reaction to sort of proceed a lot faster. So ultimately, that is sort of how a catalyst works. By finding that alternative pathway, you know, it lowers that activation energy. So instead of going up and over the hill, you're like the road runner where he finds the trap door in the hill, right? It goes to the other side and he can get there before the coyote gets him, right? And all that good stuff. Watch cartoons, it's good. So by finding that alternative pathway, you obviously get to the other side much, much quicker. So what we do see is the activation energy decreases, The result of that is the rate constant will increase and the overall rate will also increase of a catalyzed reaction versus an uncatalyzed reaction. In most cases, when people talk about a catalyst, they do speak of it as, sort of speeding up a reaction. There are sometimes situations where you might want to slow down a reaction. So there are what are sometimes referred to as negative catalysts, which you could add that the opposite is true, is sort of slows down the reaction from occurring. But probably 9 times out of 10, if somebody said, I added a catalyst, what was the purpose of it? It is to sort of speed up that chemical reaction. Catalysts can be kind of like mixtures. They can be heterogeneous or homogeneous. And just like a heterogeneous mixture, you see different layers. A heterogeneous catalyst means that basically the reactants and the catalyst are in different phases. So maybe the catalyst is a solid and everybody's aqueous or a gas. The Haber process for ammonia, the production of nitric acid, and catalytic converters, which we have in our car, or most of our cars, have basically a couple of chambers where it basically converts a lot of hydrocarbons as it goes through the tailpipe into less sort of toxic stuff coming out into the environment. Homogeneous catalysts, on the other hand, are basically catalysts where everybody's in the same state. Acid catalyst or base catalyst, a lot of times you will see on top of the arrow simply like H plus written. H plus is sort of a generic form for an acid and an acid catalyst. Kind of like the lab we did today, right? HCl is really a catalyst in that case, and it is in the same state, right, as all the other ones that we used in that experiment. It's all in the aqueous sort of environment. So sometimes catalysts like that, acid or bases, sometimes you really need a specific sort of pH to make everything sort of function and move really well and more efficiently. And that's a lot of times why we use sort of acids and bases as catalysts. So here's the catalyst, for example, in the Haber process where we make ammonia. The production of ammonia, or the reaction that makes ammonia, is a spontaneous process, which means, frankly, it occurs. It actually occurs really, really slowly if you just let it happen. So to speed it up, they obviously add here some iron, some aluminum oxide, some solid catalyst. And as you can see here, it actually does a couple of functions. It sort of directs all of those guys towards a central location. It actually aids in the breaking of a lot of those bonds and allowing them to sort of reassemble in a much more efficient manner, and allows it to obviously occur a lot faster. This is the process of making nitric acid, which is actually a several process event here where we use platinum there as a catalyst. We make some NO, which then can combine with oxygen to make NO2, and then ultimately make our nitric acid. We also make nitrous acid as well as sort of a byproduct. The nitrous acid actually can then kind of feed back into here and sort of provide some NO2 as well. So it kind of circles around in that case. Here's our catalytic converters in our cars. And again, if you ever went through a smog check and failed, that's hopefully not your issue. Or if you ever got to your car and found it no longer there when they take it and steal your catalytic converter. They steal your catalytic converter because inside is a lot of nice metals that are used as catalysts for these reactions and stuff like that. Honeycombs of different metals and stuff like that. So in this case, basically the products here is to stop unburned hydrocarbons, which are carbons and oxygens, and cut down also on some nitrogen emissions as well. Any questions on catalysts or kinetics? Okay, so we're then going to go to chapter 13. Just give me a second here to. Okay, we are off to chapter 13 here, which is equilibrium, chemical equilibrium, and this is the topic of the class. Basically, we're going to talk about every single equilibrium that you never ever want to know about. And this part of the class is brought to you by the letter K, which is the equilibrium constant. And again, we're going to hit every single K known to man as we go through chapters here. So let's talk a little bit about chemical equilibrium. Chemical equilibrium really involves a certain type of reaction, and it involves that reaction like we just saw a second ago. It involves reactions where you have, say, A plus B goes to C plus D. And these are reversible reactions. Because they kind of have arrows heading in both directions. And because they have arrows heading in both directions, what it means is this reaction will actually happen in both ways. It will go in, again, what is referred to as the forward direction, which is going from reactants to products. At some point, you will build up enough products that the products will decide we would like to react with each other and head back the other way. And when that occurs, that is what is referred to commonly as the reverse direction. So in a reversible reaction, there's always sort of a forward direction and there's always a reverse direction. Eventually, what will happen in a reaction like this is it will reach what is known as chemical equilibrium. Now, chemical equilibrium does not mean what a lot of people think it means, which is equilibrium equal. I have an equal amount of everybody on both sides. And that is not what chemical equilibrium means. As we'll talk about, pretty much what chemical equilibrium means is we're actually talking about the rate, the kinetics of what's going on. And what that means is at some point, the rate of the forward direction will eventually equal the rate of the reverse direction. So just as fast as it goes from reactants to products, it will turn around and come back from products back to reactants at exactly the same rate. What that means is you don't necessarily get the same amount of everybody on each side. But what does happen when something reaches chemical equilibrium is it pretty much locks everybody into place in terms of their concentrations, right? So if everybody locks in at equilibrium, if I lose a little this way, but it comes back exactly the same amount and same rate, nothing's really going to change. So that is what is meant by chemical equilibrium. It means when the state of equilibrium is reached, whatever all the reactants concentrations were at that point, what the products concentrations were at that point, they're going to be pretty much locked into place and not going to continue to change because just as quick as it goes one way, it will just as fast go back the other way. Any questions on that? Does that mean that you'll never get the same concentrations on both sides of the arrow? You could, but it doesn't mean that you always have equal amounts on both sides. So chemical equilibrium is when the concentrations of all the reactants and the products, basically because they get locked into place, will remain constant until you do something to screw it up, which is what we'll talk about at the end of this chapter. But if you don't do anything to screw it up, the reaction will pretty much be done in a sense. That is the other kind of interesting thing about a reversible reaction, which is you may look at it in a beaker and go, all right, my reaction turned red. I'm done, right? There's not much going on. The reaction is over. Nothing else is happening. So on sort of the big scale, the macroscopic scale, it may look like there's absolutely nothing going on. It turned red, or maybe it went from red and turned colorless. You know, it looks like it's over. But if we were to sort of zoom in to that beaker, you would see a lot of activity. You would see A and B go into C and D. You would then see C and D going back to A and B. And it takes a lot of that constant forward and reverse reactions occurring to basically maintain something that looks like it's over. So in a reversible reaction, even though we technically call the reaction done in a lot of cases, it's really not done. It's continuing to go back and forth. It's just really not much is changing overall because it's going back and forth from reactants to products or products to reactants, basically at the same rate, which means there's not much that's going to change overall. So the overall sort of appearance may appear that not much is happening. So that's what it means on the macroscopic level. It looks static. It looks like not much is happening. But again, there is a lot of activity that's actually happening on the microscopic level, the molecular level, to really keep that sort of reaction at equilibrium. Any questions on that? So graphically, if we look at this reaction, which is a little N2 plus H2, going to give us our ammonia. Guess I'm a chemist, so I should put some numbers here. Do those numbers. So what we see at the beginning here, our reactants are our N2 and our H2. And we see at time 0, pretty much that is all we got going on. At the time 0, there's really no products that have been formed. So what's going to happen in this reaction is pretty much at the beginning of the reaction, we would expect it all to be heading towards the products in the forward direction. So at the very beginning here, we would expect it to head towards the product side. That means in terms of the concentration of the reactants, should they start increasing or decreasing at the beginning here? If the reaction is going from reactants to products, the reactants should start to decrease. And that is what we see in this graph. We start to see that the reactants are starting to decrease. And at the beginning of this reaction, we then should start to see the products increase, right? Because we're starting to make some products, right? And we're starting to make some products, and that's what we see here. We do see it starting to increase. Now, this is going to continue, and pretty much the forward direction of this reaction is going to pretty much be the dominant thing that's occurring here until a point where we sort of build up enough of our products that we have a good amount of products where it could actually start going back in the other direction. So at some point here, we're going to start initiating the reverse direction occurring at this point. And the reverse direction will cause our products to go back. At that point, what we should actually start seeing in terms of our products is it really shouldn't be increasing as fast, right? Because now we're sending some of them back the other way. And that's what we see right about here, right? It's starting to sort of level off the amount of products that we're making. The other thing that we should also see is at this point, the amount of reactants actually should also start leveling off, because even though we're using them to make products, we're now sending some reactants back the other way. And we kind of see that here. It's not as steep of a decrease happening, you know, as we're increasing and starting that reverse reaction. At some point, we will reach a situation where the concentrations of everybody will essentially flatline. If I could draw a straight line, it will essentially flatline straight across there. And that basically means at the point where they all flatten out, that is the point where we have reached chemical equilibrium, because the only way for all of them basically to just start flattening out and not really changing concentrations is that we hit the point where that rate of that forward reaction equals the rate of the reverse reaction. And it's right there where pretty much everybody flatlines out. Any questions on that there? Yes. Yeah. There is. So the reaction is still going on. It may visually not look like much is happening. And the reason it's not looking like much is happening is, you know, basically just as quick as you like dump some products to the other side, those products are going to recombine and come back just as much. So it's going to kind of really keep yourself balanced in that sense, right? So overall, you know, if somebody took like a peanut and threw it to the right, and then somebody on the right threw a peanut back, you still have like the same amount of peanuts on both sides ultimately, right? And nothing's really changed as a result of that, because it happens pretty much equal to each other. So like as they're traveling, they're kind of crossing in the night, if you will, like two cars, right? They're passing each other, and you know, they end up at the opposite sides at the same time, and you basically just replenish what you lost. But there's still the reaction sort of occurring at this point, and that's the important part of that. It's actually the rate of each of those things going forward and reverse that are equal to each other. That is what is meant by equilibrium. Not that, you know, we equal out the sides in terms of how much, but it's because it goes back and forth at the exact same rate, pretty much nothing changes. And that's what we see there at the back end of this graph. That means that pretty much everybody's concentration, wherever their concentration is, will basically be locked into place. And it really will not change any greatly unless you did something to kind of screw up that equilibrium, which we'll talk about at the end of the chapter. And the other point of that is, if we look at where everybody's final concentrations are here, if you want to talk about it in the sense of that, they are different in terms of the concentrations of everybody, but they're not changing at that point when chemical equilibrium rates reach. They're basically locked into that sort of number. Any questions on that there? So again, here initially in this particular reaction, we have no products that are formed. It's not until we start basically decreasing some of these guys that we will see an increase in some of our products. And then eventually we'll get that reverse reaction occurring, and eventually we'll reach equilibrium. And that again is what we see here, pretty much where everybody flattens out. That point where that occurs is where we reach that equilibrium. The forward reaction is pretty much dominant at the beginning here in this type of situation. The reverse reaction needs a little time to sort of build up concentration to get it going. But at some point, those rates will eventually equal each other, and we'll reach chemical equilibrium. All right, so if we had this particular reversible reaction and we decided we're at equilibrium, we decided we wanted to add more H2O to the flask here. Take a second and think about, how would the concentrations of everybody change? Would they go up? Would they go down? Will they stay the same? So you have the system at equilibrium, you add some more H2O to it. Think about what happens to every single one there, every single substance. Concentration go up, concentration go down, does it stay the same? We'll talk. Okay, so let's talk about it. We have this system, we're at equilibrium. Now you decide to add more water, right? H2O to it. What is going to happen? Let's start with the amount of H2. Will it go up? Will it go down? Will it stay the same? What do we think? I think he's pointing up, so I think that is what he's trying to indicate. That's good. He used the right finger there to point up with that. So we're going up in that case. So why would it go up? We are adding H2O, which is on the left-hand side. When I add H2O, I am now really increasing the amount of reactants, and that should really kick off the forward direction, right? So by doing so, what would happen here is you obviously provided a lot more H2O flying around, which means it's going to be able to find some CO, and it's going to initiate that forward direction occurring. The result of that is we should see an increase in our H2. What about the CO2? We should see a increase in that as well, as it's also a product. How about the CO? What would happen there? It should go down, because remember, the only way to make our products is we have to use up our reactants. So we would expect to see the H2 start to drop. How about our good friend H2O, which we added? What would actually happen with that? Well, what would happen with that is, frankly, you added it, so we would expect it probably to go up, right? Because you artificially added it. But once it goes up, it starts reacting. We then should start to see it go back down, right? As it's starting to react. Because you artificially added it, it may actually end up higher than what you started with because you threw more in there. But the general trend of what you would see with that is it should kind of peak up because you added it. Then as it starts reacting with the CO, it should start to come back down. And like I said, you may actually end up higher than you started with just because you added it artificially. Any questions on that? Yeah. Why CO decreases? Is that what we asked? Yeah, it decreases because when we add the H2O, it basically kicks off the forward reaction. And in order for the forward reaction to occur in this example, you pretty much need H2O and CO to come together, which means if they're coming together to go through the forward reaction, really both of those ultimately are going to start working their way back down in concentration because they're being used up to make products. Again, just the water there would probably be a little bit higher because we added it. Other questions on that? All right, so same thing here, except in this case, we're going to add some H2 to our flask. What's going to happen to everybody's concentrations here? Okay, here, so we're adding H2, which in this case is actually on our product side. When I add the H2, should that initiate the forward direction or the reverse direction? Should really kick off the reverse direction happening. Once again, we have a greater availability of H2 that can now react with CO2 to go the opposite way and start forming our reactants in this case. The result of that is we should see the CO2 go down. The CO should go up and the H2O would go up as well. Again, with the H2, we would see probably the same patterns we talked about on the other one. It will go up, and then as it starts reacting, it will come back down. Any questions on that? Yes. It would not, because it's basically kicking off the reaction heading to the left, which means we're basically making these guys at that point. So we should see it go up. No, so again, in this case, in order to make both of the things on the left-hand side, you need both reactants, right? So when you add the H2, it's not going to just stay by itself. It's going to go find some CO2 and do some reacting, right? The process of that reaction is going to produce CO, right? And H2O. So you would see an increase in both of those guys. In order to pretty much make products, you need the reactants to do so, both of them in this case. So in the case of this, the H2 and the CO2 would be the reactants, which they both would be used up a little bit to make those guys on the other side, and you would see an increase occurring on the left-hand side. Because the only way you can make CO would be from CO2, right? And when the H2 and the CO2 come together to make it, and that's again why you would see an increase in it. Other questions? All right, so we looked at that. So let's talk about a very important letter. And as I mentioned before, it pretty much is the letter of the class. This part of the class is brought to you by capital K, not lowercase k, as we just found in the last chapter. Lowercase k is the rate constant. Capital K is the equilibrium constant. So it is a constant value, and you could get it basically by taking the concentration of your products divided by the concentration of your reactants. And that is what we see here. Concentration of NO2, and here we actually do use the coefficient as the exponent there. So that is where the 2 comes from, divided by the reactant, which is NO2. Coefficient here is 1, which is why there is nothing written there. In this case, it equals 4.63 times 10 to the minus 3. Not important, that particular number. In general, we write an equilibrium constant by taking the concentration of our products over to reactants. We do use the coefficients as the exponents. So we do use those coefficients as those exponents when we do it. Once again, the little bracket means concentration. And for the most part, it is molarity that we deal with here, which is our moles per liter. Now, when we calculate something like this, where we use the concentrations of everybody, they do need to be obviously equilibrium concentrations. So these has to be the concentrations of everybody once that reaction reaches equilibrium. And it is sometimes referred to as Kc, C for concentration. Very creative. I know. It is a constant value for a particular reaction, the way it's written, and at a particular temperature. Really, the only thing that affects the value of the equilibrium constant is temperature. So if you keep the temperature the same, you could do the reaction many different ways, many different times. You will always get the same equilibrium constant as long as the temperature remains constant. And what I mean by that is you could do a reaction like this, like A plus B goes to our C plus D. Maybe in the first experiment, you use like 4 molar of this guy, 4 molar of this guy, 0, 0 of that guy. Maybe in another experiment, you use like 2 molar, 0 molar, 1 molar, 0 molar. Maybe you use all products, maybe use all reactants, a combination thereof. It really doesn't matter how much you start off with each of those things. It will always come to rest at equilibrium with the same proportion of products to reactants, regardless if you started with all reactants in that experiment, or you did all products, or you did a little bit of each, or less reactants in one trial versus the other. It doesn't really matter. So sometimes people think, well, I used a lot more concentration in this trial versus this trial. The equilibrium constants should be different, and they will not be different. They will always, again, hit the same ratio of products to reactants as long as you keep the temperature the same. Now, if you do change the temperature, the actual value of the equilibrium constant will change, but it will still remain constant. And what I mean by that is, if you did an experiment at, say, 25 degrees Celsius and you calculate a bunch of equilibrium values, constant values, they would all be the same at 25. If you then did the exact same reactions, but at, say, 45 degrees Celsius, and you calculated the equilibrium constants at 45 degrees Celsius for the exact same trials, the exact same runs that you did at 25, all the K values at 45 degrees would be the same. But if you compared the K values from 25 degrees to 45 degrees, those numbers would be different. So that's what we mean when we say we change the temperature, the value of the equilibrium constant will change, but it will still remain the same as long as you then keep the temperature the same for all those runs. Those guys should all be the same. Any questions on that there? Now, what does the value of the equilibrium constant tell us? If I have a large value of K, does that mean when I reach equilibrium, would I mainly have reactants or products? It would be, right? Because in order to get a large value mathematically, right? Top number would have to be large, bottom number would be small. That would give me a large value. So if you have a large value of K given to you, it tells you that when that reaction reaches equilibrium, you would expect to have mainly products present. And vice versa, if you had a small value of K, the only way to get a small value of K in this case would be products would have to be small, reactants would have to be a large number, right? If you take a large number on the bottom and a small number up on top and you divide them, you end up with a small number. So if you have a small number for the equilibrium constant, it will tell you that when you reach equilibrium, you mainly have reactants that are present. So what is considered a large value and small value? A large value is that big number of 1. Yeah, so anything 1 and above is considered a large value of K, which means you would expect mainly products to be there at equilibrium. Anything that is less than 1, like has a negative exponent, like times 10 to the minus 3 or something like that, or like the one we saw on the previous slide, like 4.68 times 10 to the minus 4 or 3, whatever it may be. Those are considered small, and when you reach equilibrium, you will mainly have reactants present. One really nice thing about the equilibrium constant is it is frankly just a number. There are no units. So you don't usually use units for the equilibrium constant, unless you're strange, but some people do, I guess. But most people don't use units for the equilibrium constant. It is just a number. And once again, that number gives you a very good understanding of the reaction and what you should expect to happen when it reaches equilibrium. We mainly have products or reactants present. Any questions on that there? So for example, here, if we take this one where we got Mickey, and it reacts with a couple of dots there, and Mickey gets turned upside down. And we have the equilibrium constant here of 25. What would be expected at equilibrium, where we mainly have reactants or products there? We should expect to have products. Again, a value of 25 is considered a large value, and we would expect mainly products to be there. Are there extremes for those numbers? The answer is yes, as we'll go through different types of equilibrium constant values. There are certain ones that are extremely large, like numbers like times 10 to the 15 and 16, which is a super large number. And there's also equilibrium constant values for things that are extremely small, like times 10 to the minus 34, which is an extremely small number, or times 10 to the minus 20, which is a really small number. So there are variations of large and small in terms of the number. And that also tells you, obviously, if you had something, for example, that was an equilibrium constant of like 2 times 10 to the 20, right? For the most part, it's all going to be going which way? It's going to be going in the forward direction, right? If you have something like 2 times 10 to the 20. But even though you have something that is that large in terms of the equilibrium constant, and pretty much 99.99% of it, it's all going to the product side, it is still a reversible reaction, which means a very small, minuscule amount is going to head back the other way, like super, super small amount will head back the other way. So even though there is sometimes extremes that could occur with equilibrium constants, it is still a reversible reaction. It just means a super small amount will probably be heading back the other way when it reaches equilibrium, but there's still a little bit of back and forth, always happening, regardless of whether or not it is almost considered a one-way type reaction in either direction. Any questions on that there? So let's talk a little bit about homogeneous equilibrium. Homogeneous equilibrium means that everybody's in the same phase. So in this case, they are all gases, which means we can write our equilibrium constant of concentration of NO2 squared divided by the concentration of N2O4. But because these are all gases, we usually look at things like perhaps pressure with gases, like our friend PV equals nRT, right? That is our ideal gas law. That once again is the pressure in atmospheres, the volume in liters, N is moles, R is the gas constant, 0.08206. And that is our temperature in Kelvin, right? Liters, atmosphere, or Kelvin, mole. So we could also write an equilibrium expression for things that are gases by using partial pressures, and it's done the same way. This is the partial pressure of our NO2, which is our product, squared, divided by the partial pressure of N2O4. And this is not a KC anymore. This is a KP, adding to our list of Ks. We're already up to 2 and 3 slides. That is KP. P, I'm assuming, means pressure there. So I'm going to go with pressure. KC means you should use concentration. In general, for the most part, the standard unit of pressure that you should usually use in calculations is what unit? ATM. You should use ATM in most cases. A reminder, 1 ATM, right, is 760 torr, right, and 760 millimeters of mercury. There will be a calculation that we'll do a little bit later on in this chapter where you may be given pressures and they may be given to you in a different unit like torr or something like that. And they may even ask you, hey, at equilibrium, what is there with all the pressures in torr? And sometimes people think, well, they gave it to me in torr and like I'm supposed to give the answer in torr. Seems like I could just keep it in torr. But for the most part, especially when we do what are referred to as ice tables, you actually need to convert it to atmospheres, do the calculation, and then go from atmospheres to torr. So it's really important to keep that in mind that a lot of times you do need to kind of convert pressures into atmospheres when you use it in the calculation, and then obviously convert it to whatever unit it may be looking for. Now, the KC value and the KP value in most cases usually do not numerically equal the same value. So they don't usually equal the exact same number, but they tell you the exact same thing. So if you have a large value for KP, it tells you pretty much have a lot of products and you probably have a lot of gas molecules on your products, which is causing the increase in pressure. And if you have a small value for KP, it means you have a lot of reactants, which means, you know, those are really where all the pressure is happening in that particular case. So they don't numerically mean the same or tell you the same thing or tell you the same value. Let's spit that out, right? They don't numerically tell you the same value, but they do tell you the same idea of whether or not you would expect products or reactants. So we do need a way to go between the two, and that is what the formula right there is. If we take the KP value, it will equal our KC value times R, which is our gas constant, which would be this guy right there, times our temperature, which should be in Kelvin, to the delta N, which is the change in moles of gas. And that is found by taking the final minus the initial in terms of the gas molecules by taking the coefficients. So if I had 2A, that's a gas, plus B, that's a gas. And let's just say it goes to 2C, that's a gas. What would be the delta N here? So we want to take products minus reactants. So how many gas molecules are on the product side? On the product side, there are 2. Yeah, it's coefficient. Minus on the reactant side, there are 2 there and 1 there. Yeah, so that's 3. Gives you a -1. Yes. The negative here is important because mathematically speaking, if you decide I'm just going to take the difference here and go 3 minus 2 is 1. Is there a difference in the math if you do this to the 1 or you do this to the -1? Is there a difference mathematically speaking? There is, right? The -1 means 1 over it. So it's really important here. It's a very common mistake that people will just go, okay, the difference is 3 and forget about the negative part of it. But the negative part of it is really, really important. Otherwise, you will get the wrong answer. So you always, again, want to make sure that you do the moles of the gas minus the moles of the reactant. It is just the gas molecules involved here. Yes. So if you should have maybe something else in there like a solid, it would not be included or anything of that nature. In order to have a KP, you kind of need gases. Yeah. So if you have a reaction that doesn't have gases, it probably doesn't have pressure in that sense, and you wouldn't have a KP expression. So you definitely need gases involved there to be able to write a KP expression. Any questions on that there? All right. Now, in a homogeneous equilibrium, there's a couple of things that's important. First off, if we took this equation here, which is acetic acid plus a little bit of water, makes some acetate and some hydronium ion, and we wrote the equilibrium expression like we were doing before, where we take products over reactants, we would end up with an expression that looks something like that. In reality here, the water is going to remain constant in this reaction. Nothing much is going to change here because it's actually a pure liquid. So because water will be a constant, we actually do not include it in the equilibrium expression, which means that if we were to write the correct equilibrium expression for this reaction, it would actually be this guy right here on the bottom, which is the concentration of acetate times the concentration of H3O plus divided by acetic acid would be the correct equilibrium expression. In general, as we mentioned, there's no units included, but there are pretty much few things that we do not include in an equilibrium expression. One is what we see right there. Anything that basically is a pure liquid does not get included. Anything that is a solid, as we'll talk about in a bit, does not get included either. If you think about a solid, it's pretty much just sitting there, not really participating, right? Just kind of floated to the bottom. If you don't do anything to it, it will remain a solid and it really will not participate. So really, there's actually two things that we always include in the equilibrium expression. And the two things that we include in the equilibrium expression are things that are aqueous, which is like our water environment, and things that are gases. So those are really the two things that get included in the equilibrium expression, as they are responsible for some of the things that are going on. If you come across anything that is a solid or a pure liquid, you typically will leave it off of the expression. Any questions on that there? Okay, so why don't we try some here? Write the Kc and Kp for each of these, if possible. Okay, let's take a look. So for the first one here, if we were to write our Kc, would be our products, which would be the concentration of NO2. Once again, we would take it to the fourth power because of the coefficient. We would times it by O2, which basically would be to the first power. We then would divide it by the concentration of N2O5, which we would then remember to square because of the coefficient that is there. Any questions on that there? Our Kp for this one, we can write it because we got gases going on for all those. So this would be the partial pressure of NO2 also to the fourth times the partial pressure of O2 divided by the partial pressure of N2O5, which once again, we do need to square as well. So obviously, if we had the equilibrium pressures of each of these guys, we could go right into that expression and solve for the value of the Kp at that point. Once again, much like the Kc value, it would have to be equilibrium pressures, not initial pressures or anything like that. Any question on those two there? All right, last one there is we could definitely write our Kc, which once again would be the H3O plus times the F minus, which is our products, divided by our HF. And do I include the water? I don't. Again, it is a pure liquid, so it would not be included. So that would be the expression. Can I write a Kp for that one? I cannot, because there's actually no gases there, right? So we got no gases, you can't write it. You probably don't have much of pressures happening. Any questions on that there? Okay, we will lay it up, I think, there for today.